Welcome to the lecture module on optics. In the last two lectures, we have been discussing about the Young's interference experiment. We will take it a bit forward, and today we will continue and see interference with coherent and incoherent sources. So, the topic of today's talk is interference with coherent and incoherent waves. We will quickly recall what we have studied in the last lectures. So, we quickly recall that in Young's experiment we have a source S here passing through a aperture here which is a small hole, and there are two more apertures S1 and S2 here, and the waves which are emanated from S1 and S2 interfere on a screen which is here. Depending on the path difference, that is R2 minus R1, we may have interference maxima and minima. We have discussed this in detail. So, S1 and S2 are point sources drawn from the same wavefront. Please see, there is a point source here and these two are drawn from the same wavefront. These blue curved circles represent the wavefront here, and as you can see, the wavefront reaches S1 and S2 simultaneously, and S1 and S2 are drawn from the same wavefront. That means they are from the same phase front, or S1 and S2 are in phase. In phase means with the phase term here cos omega t without loss of generality. If I assume that this is x equal to 0, this is z equal to 0, then we have A1 cos omega t and psi 2 is equal to A2 cos omega t. The phase term is the same, they are in phase. Now, we see that we recall the conditions for bright and dark rings that we have already derived in detail. The conditions for bright and dark rings at the point P here, psi 1 is equal to A1 cos k R1 minus omega t, R1 is this distance, and psi 2, that is disturbance due to the second source S2, is A2 cos k R2 minus omega t, and delta therefore is the phase difference. This is the phase term. So, the difference between them is simply k times R2 minus R1, and R2 minus R1 is the path difference. We have also seen that whenever R2 minus R1 is equal to plus minus n lambda, where n is an integer, it is the condition for bright fringes. At points P where R2 minus R1 is an integral multiple of the wavelength, then that condition is that point would be bright, and whenever it is n plus half times lambda, then we have the condition for dark fringes, where n is equal to 0, 1, 2 and so on. The plus sign here represents the fringes, the maximas and minimas on one side, and minus sign represents maximas and minimas on the other side. At the point O, where R1 0, I have shown it as R1 0 and R2 0 are identical, because this is a perpendicular bisector of S1 and S2, and therefore, R1 0 is equal to R2 0, the path difference is 0, and that corresponds to a maxima which is called the 0th order bright fringe. We have discussed all these in detail in the previous lecture. So, we now look at a different situation, slightly different situation, where the source S has a finite offset. So, here is the new discussion that we want to make, that the source S, if the source S here, so let us look at the diagram first. So, if the source S has a small offset, it is not along this line here, instead the source S, now I am calling it as S dash has a small offset, it is a little bit upward here, and then obviously we see that the distance S dash S1 and S dash S2 will be different, because there is an offset. In terms of the wavefront, what we note is that when the wavefront, look at the blue wavefront here, when the blue wavefront reaches this plane, the plane containing the apertures S1 and S2, we see that the wavefront has reached the point S1, but it has not reached the point S2, the blue one. So, the wave front has not reached the point S2. It will reach the point S2 at a later time. So, the wave front here has reached S1, but it has not reached S2. It will reach S2 at a later time. It means the wave front here is lagging, it is lagging in phase. At a later time it will reach here, and therefore, there is a initial phase difference of delta phi, del phi here between delta phi between the sources S1 and S2. Please see that the wave front would reach here at a later time, which means, let me explain this. So, which means if I had cos omega t as the initial phase, then we will get the same wave front at S2. This is at S1. At S1, I have dropped the amplitude. At S2, the same wave front will come at a later time, or when I have a phase term cos omega t as S1, we have the phase at S2 will be cos omega into t minus delta t. That is, at that instant on the plane here, one wave front, the wave front has reached here at the point, but at the second point here it has not reached. Now, I have expanded, enlarged it a little bit. So, this is behind, or at this instant, at a particular instant when this is in phase, the phase front of the earlier travelled wave would be like this. In other words, this phase front will reach here at a later time, or at a given instant the phase at S1 and S2 are related by this. In other words, we have the phase as S2 as omega t minus omega times delta t, and this one I am calling as delta phi. And therefore, the phase difference between the two S1 and S2 will be equal to omega t minus omega t here. So, phase difference. So, omega t will cancel. So, we have omega t minus delta phi. Delta phi is this phase lag. So, this is delta phi, and therefore, we have delta phi. That is why I have this term here, that I have shown that this, the second wave has k r2 minus omega t plus delta phi. There is a phase lag which is delta phi. So, delta phi is the initial phase difference, it is the initial phase difference between the two waves. It is also shown here in a different way. The blue wave front, as we can see, it has, at this point the blue wave front has reached, the red wave front will come at a later time. Although I have shown it in front, blue has passed by and the red wave front has reached here, and therefore, the red wave front is behind the blue one, and there is a phase lag of delta phi. The phase lag is the same delta phi here, and therefore, the net phase difference is now not just k r2 minus k r1, but also there is a phase difference of delta phi. All of this is because S dash is offset here, therefore, this propagation distance is different from this propagation, this is smaller compared to this, and therefore, at the point O, now therefore, at the point O, R1 is equal to R2. So, this distance is the same, R1 is equal to R2, but delta is not equal to 0. At the point O, R2 is equal to R1 here, but delta phi remains, and therefore, at the point O, delta is not equal to 0. If delta is not equal to 0, we will not have the 0th order bright fringe here. Delta may be 0 somewhere else, the phase difference may be 0 somewhere else, and therefore, the 0th order bright fringe will not appear at O, because there is a phase difference at O. Let us look at this a bit more carefully. So, let me put the condition for bright and dark fringes again here. So, let us see at the point P, at a general point P, we know that psi 1 is equal to A1 cos k r1 minus omega t, and psi 2 is equal to A2 k r2 cos omega t. that is this, I am showing only this, and delta is the phase difference k r 2 minus k r 1, and r 2 minus r 1 is the path difference. We have already seen this in detail, and r 2 minus r 1 is equal to plus minus n lambda is the condition for bright fringe and the condition for dark fringe here. So, this we have already seen. Now, with the delta not equal to 0, so let me show this slide now. So, this slide we have seen, and I have shown that there is a finite delta phi here, and at this point delta is not equal to 0. So, let me take this here. Therefore, for delta is equal to 0, k into r 2 minus r 1 is equal to minus delta phi. Please see that for this to be 0, this will be equal to minus delta phi, and that is what I have written, which means r 2 must be less than r 1, and therefore, I have shown a point O dash here where r 2 is less than r 1, and at this point O dash, the point O dash is such that S dash S 1 plus S 1 O dash, that is the total path here, path length is equal to S dash S 1 plus S 1 O dash if it is equal to S dash S 2 plus S 2 O dash, then we have path difference is such that delta phase difference is equal to 0. So, the position of the 0th order maxima or the central fringe will be shifted to a new position, which is O dash. Therefore, the condition for maxima is delta is equal to k r 2 minus r 1 plus delta phi is equal to plus minus n 2 pi, n times 2 pi, or r 2 minus r 1 is equal to the path difference, which is equal to, I have taken the delta phi to the other side, and we have divided by k everywhere, and therefore, k is 2 pi by lambda, therefore, lambda by 2 pi is here. So, we have divided by k. So, n times 2 pi divided by k minus delta phi divided by k. We have taken this, and therefore, we have the new condition now that the path difference r 2 minus r 1, r 2 minus r 1 is equal to n lambda minus delta phi by 2 pi into lambda for the nth maxima. There is an extra term now because of the finite delta phi. Please see that if delta phi is equal to 0, that is if this were on the perpendicular bisector here, the original position S, then we would have had delta phi is equal to 0, and the condition remains as path difference is equal to n lambda. Now, there is an extra term which depends on the phase difference. What is the effect of this on the fringe width? Let us see the effect of this on the fringe width. So, for the nth bright fringe here, so let us look at this. Let us look at the, for the nth bright fringe, if delta phi is a constant, then path difference r 2 minus r 1. So, this difference we have already calculated in terms of the x coordinate there. So, it is x n dash d by d. For the nth fringe, if n x n is the coordinate x n dash, I have written x n dash just to distinguish that now we are dealing with a case where there is a finite delta phi, that is all, otherwise it is the same x n as before. So, for the nth fringe, the condition we had earlier derived was x n d by d equal to n lambda. Now, because the position of the nth maxima has changed, I am calling it as x n dash. So, that is equal to n lambda minus c, where c is that constant, that is delta phi by 2 pi into lambda. So, please see that we had n lambda minus this constant I am calling as c. If delta phi is a constant with time, then this is a constant c, and therefore, n lambda minus c, where c is a constant. For the n plus 1th fringe, that is for the next fringe, it will be x n plus 1 d by d is equal to n plus lambda minus c, because c is a constant. So, dash is only to represent the next the case where there is a finite delta phi. It is not derivative or anything, and therefore, the fringe width beta is equal to x n plus 1 dash minus x n dash. So, from 2 and 1, if we subtract this, then we have d by d into n plus 1 lambda minus c minus n lambda plus c, which is equal to, this is the fringe width, which is equal to d by d into lambda. As before, I have written here as before. As before means the case when there was no phase shift, no initial phase shift. That is the case when the source S was on the perpendicular bisector. There is no change in the fringe width, even if there is a offset in the source, but the fringe pattern is shifted. The fringes are shifted, the fringe width remains same, which means the fringe pattern is shifted. For example, if we have all linear fringes, bright dark, the entire pattern is shifted, otherwise it looks identical. Now, that is the fringe, there is a fringe shift, each fringe is shifted, but no change in beta. So, what does this mean? Let us calculate this first. What is the fringe shift beta in terms of the geometry? So, let me calculate the fringe shift. Therefore, the fringe shift here, the fringe shift is given by x n dash is the new position of the nth order bright fringe in the presence of a constant phase difference delta phi between S1 and S2. So, x n dash by d is equal to this condition. Remember that x n into d by d was equal to n lambda when there was no phase shift, when there was no delta phi or delta phi was equal to 0. Therefore, for n lambda I am substituting x n d by d, the original position of the nth bright fringe. Now, the nth bright fringe has changed to a new position x n dash, but the original position x n is here, and then this into d by d is n lambda. Therefore, we have replaced this by this minus c, which means if I take the x n to the other side, x n minus x n dash, that is the fringe shift, the shift of the nth fringe x n minus x n dash by d is equal to c, the constant, which is equal to delta phi by 2 pi into lambda, or the fringe shift delta x n, this is the fringe shift delta x n is equal to delta phi by 2 pi into lambda d by d, and lambda d by d is the fringe width, and we have seen that the fringe width does not change whether delta phi is 0 or delta phi is a finite number, and therefore, we see that this side is independent of n, whether it is the first fringe or fourth fringe or fifth fringe, it does not matter. It simply says the fringe shift is given by delta phi by 2 pi into beta. What does this mean? This means that the fringe shift delta x, now I drop the n because it is independent of n, therefore, the fringe shift delta x is equal to delta phi by 2 pi into beta. It depends on delta phi. This is now completely understandable. We can see that if we put delta phi here is equal to 0, then delta x is equal to 0. If delta phi is 0, delta x is equal to 0, means there is no fringe shift, and if delta phi is a finite number, then there is a fringe shift. For example, if the phase shift is 2 pi, delta phi is 2 pi, then delta x is equal to beta, which means the bright fringes would shift by 1, that is nth fringe will take the position of the n plus 1th fringe or n minus 1th fringe, depending on whether it is to that side or this side. So, the fringes would shift by delta x is equal to delta phi by 2 pi into beta. Let us see the geometry of the problem more carefully now. So, we will see the geometry of the problem. When the source is offset, so let me first show only the geometry here. So, this is the geometry of the problem. Original position was S, which is on the perpendicular bisector here, S1 and S2 symmetrically about this line SO. Now, the source has shifted to a position S dash, and therefore, we have the fringe shifted to a new position O dash, and the path difference, total path difference will be 0 if this plus this equal to this plus this, then the net path difference will be 0, and O dash will be the new position of the central fringe corresponding to delta equal to 0, path difference equal to 0. So, S dash, there is the offset here is L, we denote it by small l. O dash is x, that is O is here, O dash is x dash is nothing but delta x, because x position is 0 originally and the new position is x dash, therefore, delta x is equal to x dash, the coordinate of the new position of the central maximum. S1, S2, the separation here is d, small d between the two sources, and L, let L be the separation between these, and d is of course the distance to the screen from the two sources S1 and S2. And therefore, now let us see that for the central fringe the path difference is equal to 0 if the condition this plus this is equal to this plus this, the length here are equal, which means I can take this S2 O dash to the other side or S1 O dash to this side and write S2 O dash minus S1 O dash, S2 O dash minus S1 O dash, this separation is equal to S1 S dash, S1 S dash minus S2 S dash. So, that is nothing but S2 O dash is R2, R2 minus R1 is equal to, I am denoting this as Q1 and Q2 is equal to Q1 minus Q2. So, R2 minus R1, we know the path difference between these in terms of the separation here, this and d, and that is x dash d by d, x dash is the position here of O dash. So, R2 minus R1 is x dash d by d. Similarly, Q1 minus Q2, Q1 minus Q2, just like this, Q1 minus Q2 will be equal to L, the offset, divided by L into d, because it is from this triangle, this part difference. We had calculated from this part difference, now we are calculating from this triangle, and that is identically L by L into d. This implies, please see here, this implies that x dash by d, so d is common, and therefore, x dash by d is equal to L by L, x dash by d, x dash by d is this angle theta, the angle theta, tan theta is equal to x dash by d. Tan theta of course is very small here, because the fringe shift is much smaller, this is of the order of 100 centimeters, 1 meter, and the fringes are only moving a few millimeters or so. So, this is x dash by d is very small, even if we do not make the approximation, it is valid, because x dash by d is tan theta and L by L is tan theta dash here. So, I have shown theta dash here, this angle tan theta dash, and they have to be equal. So, tan theta is equal to theta dash, which means if theta is equal to theta dash, that simply means that these are opposite angles, which means that S dash O dash is a straight line passing through the point M here. So, we have x dash by d, this divided by this is equal to the offset L divided by L. So, S dash O dash is a straight line passing through M. Now, let us see now the fringe shift now in terms of, we see the fringe shift now in terms of the geometry, that is the offset. Earlier we have seen the fringe shift in terms of the phase shift delta phi by 2 pi into beta. Now, we see we get an expression for the fringe shift in terms of the offset. So, let us see that. So, here fringe shift due to the source offset. So, we have L as the source offset here, and delta x is equal to x dash minus 0, 0 is the original position which is the fringe shift, and we have just shown that x dash by d is equal to L by L, and therefore, delta x, x dash is delta x, the fringe shift delta x, the fringe shift delta x is equal to d by L into L. In other words, if an offset is given, if it is given to you that the source S is offset by a certain amount and the corresponding separations d and L are given, then you can determine what is the fringe shift. So, it is the fringe shift due to source offset by L. Take an example, put some numbers, typically d is about 100 centimeters, this could be tens of maybe 10, 20 centimeters. I have taken L is equal to 10 centimeter. For an offset of 1 mm, just 1 mm offset here. So, this is the perpendicular bisector. An offset of 1 mm leads to a delta x, a shift of 10 mm here, 100 by 10 into 1, that is 10 mm, almost 1 centimeter shift. A typical idea to see how the fringe shift takes place. In other words, if you are setting up the experiment, if the source S is not exactly normal and on the perpendicular bisector here, if there is a small shift, then the central fringe will shift to this side. The same thing would happen if instead of the source moving to this side, if the source had shifted offset to this side, then we would have got O dash here, that is the central fringe would have moved here. The same thing would also happen. So, let me show you, the same thing would also happen if I have, so the source is right on this, source is here, but the S1 and S2, there is an offset between S1 and S2, that is S1, the perpendicular bisector is here now. This is shifted a little bit to this side. Then also we will have a corresponding fringe shift, because now the distance S to this and S to S1. So, S to S1 here and S to S2 will be different, and correspondingly there will be a phase shift of delta phi between the sources here. The wavefront which is reaching here will be at a different time, the wavefront will reach here. Therefore, there is an initial phase shift of delta phi, and correspondingly we will have the fringe shifted here, which will be on the line here joining this. So, the fringe will be shifted to a new position O dash. If it is, if this aperture is shifted downward, then the fringe shift would occur here. This kind of shift is called the lateral shift. It is because the alignment, there is an offset either in the source or in the double hole aperture, then we have a corresponding shift in the central maxima, and this is called lateral shift. So, here we are, the fringe shift will also occur, let me come back, the fringe shift will also occur if the aperture plate Q dash is offset with respect to this line SO. This type of fringe shift is called lateral shift. Why I am discussing this is, we will soon see another type of fringe shift. A fringe shift because of, let us say, introducing a delta phi due to an external plate. For example, if we introduce a glass plate on one of the paths, we will see that there will be a fringe shift. So, this fringe shift is simply because of the offset, not because of introducing any other thing. The offset introduces a constant phase shift of delta phi, and due to which there is a fringe shift which is called lateral shift. Therefore, just let me summarize what we have seen. So, summarizing the fringe shift issues, the fringe shift delta x due to a constant phase difference delta phi. If there is a constant phase difference, why I am insisting on constant is next I will take up when the phase difference is changing with time. So, the constant phase difference delta phi, including the delta phi could be 0 between the interfering waves, then there can be sustained observable interference fringes. When delta phi is 0 or constant, we will have a sustained observable interference pattern. The phase difference is 0 means the interfering waves are in phase, and if the phase difference is pi, we call it out of phase. Here I have shown this, that waves with a constant delta phi among them are called coherent waves. So, I have shown here delta phi is equal to 0, which means whenever the first wave is maximum, second wave is also maximum. So, this is phi or time. So, the maximas are coinciding, the minimas are coinciding, that is crests and troughs come at the same time at any given position. If the phase difference delta phi is equal to pi, it is a constant, but it is pi, then we have the crest of one wave corresponds to the trough of the other wave at that point. The phase variation, what I have plotted is the phase variation of the two waves with time. So, at any given point, if the crest of one wave coincides with the trough of the other, it means the two waves are out of phase, and the net amplitude we have already seen in another chapter, that the superposition of waves, the net amplitude will be the sum of the amplitude, which will be 0. And if there is a constant phase shift delta phi here, which means the waves, there is a constant phase shift, all the three cases correspond to coherent wave. Whenever delta phi is a constant, we will be able to see sustained observable interference fringes. This is the first point. The second point that we have is the central fringe here and all other fringes. Let us look at this. The central fringe and all other fringes would shift by an amount delta x, which is proportional to delta phi, but the fringe pattern and the fringe width does not change. Delta x is equal to, we have derived this, delta x is proportional to delta phi, but the fringe width remains the same and the fringe pattern remains the same. Now, therefore, there is a question how to measure the fringe shift in practice, particularly when delta phi is several times 2 pi. In practice, we see a fringe pattern as I showed earlier, let us say bright and dark linear fringes. The fringes are shifted because of a finite phase difference delta phi, but how to measure the fringe shift, because it looks identical, and if the phase shift delta phi is let us say 8 pi, then 4 fringes will be shifted. So, we do not know where is the central fringe now. So, how to locate the position of the central fringe, because they all look identical, all the fringes look identical, and the fringes have been shifted exactly by 4 fringe, which means the pattern again looks the same. How to locate the central fringe? The answer here is use of white light interference. We will discuss this shortly. But before we go to white light interference, I want to come to the next question, that is, what if delta phi varies randomly with the time? What if delta phi varies randomly with time? It varies with time means delta phi is a function of time. Till now I had assumed a constant delta phi, but now it is a function of time at any point. And when do we have such situations where delta phi is varying with time? We will discuss this in a minute. If S1 and S2 are two independent sources or derived from an extended source, then we will see that delta phi will be varying randomly with the time. So, let me discuss this a little bit more. So, let us look at light sources and waves coming out. So, if I have a light source, there is a light source here, a bulb let us say, and this is giving out light radiation. We know that in any particular direction, light comprises of waves which are travelling, but these waves are not sinusoidal from end to end. The electromagnetic wave is not sinusoidal end to end, because it depends on the mechanism of generation of light. For example, if we take a sodium lamp, let us say this is a sodium lamp, Na lamp. There are sodium atoms which are excited. So, if I consider the ground state of sodium is here. So, this is 1 is ground state and 2 this is energy axis. So, I am plotting the ground state and the excited state. Sodium atoms are excited here by electric discharge, and the excited sodium atoms come down, that is they get de-excited and come down to a lower energy level, and the energy difference here is given as a photon or an energy packet of energy h nu, which is equal to the energy difference. If I say that the energy here was E 2 and energy of the first level was E 1, then h nu is equal to E 2 minus E 1. We know this, we have already studied this. So, energy is given in terms of photon packets. Now, these are not infinitely extended, because infinitely extended means it will contain infinite energy, and therefore, these are finite wave trains which are emitted. So, we have continuously excitation taking place and de-excitation taking place, emission of photons coming out of the sodium lamp, and these are therefore wave trains which are travelling of up to a finite duration. It means if I take several wave trains, so let me plot several wave trains. So, one wave train is this and another wave train, they are emitted at different times. There are continuously atoms getting excited, atoms getting de-excited. So, they are emitted continuously at different times, which means the sine waves originate at different times. All of them are of the same wavelength, but they are emitted at different times, and therefore, if I look at, so these are the different waves which are travelling, individual waves corresponding to photon. So, all of them are of the same wavelength lambda, same lambda, but they are discontinuous. So, if I look at two waves, any two waves, let us say there are two waves. So, let me consider two waves 1 and 2, these two waves. Over this period, you can see that there is a constant phase difference between them, but after some time there is another wave which is here, which has no phase relation with this. So, this is time axis. So, with the time we see that over a certain time period there is constant phase difference, but if I look at the time here, the phase difference between these two waves is different from the phase difference between these two waves. This may be coming from the source S1 and this may be coming from the source S2, and therefore, there is no phase difference, the phase difference changes with time. In other words, delta phi is a function of time. Let me come back to this and now show the diagram of the, let us look at the Young's double slit experiment now. This is the same sodium lamp which is giving out radiation here, and we have the double slit here. So, I am showing the double slit S1 and S2. This is an extended source, this is not a point source, this is an extended source, and therefore, there are wave fronts where the wave fronts have no correlation. What do I mean by that? If I have a point source, this would give spherical wave fronts like this, and if my aperture is here S1 and S2, we see that this is S1 and S2. We have emphasized several times that the wave front reaches at the same time to S1 and S2, but if there are, this is not a point source, but an extended source which comprises of number of point sources which are radiating independently, then the wave which is entering here and the wave which is entering here have no phase relationship, no fixed phase relationship. It changes with the time, which means delta phi is a function of time when the source is extended source. That is why in Young's experiment what did we do? We have a point source, there was a first aperture here. This was acting as a point source which was giving out spherical wavelets which are here, and we placed the second aperture here with the two apertures, the double hole or double slit is here. Before that there is a single hole which is like a point source. We did not place an extended source directly in front of this, or nor even this, that you take two S1 and S2, two holes, and we keep one bulb. Let me show the bulb like this here, which is giving light, and another bulb here in front of this. So, this is giving light. So, what is the point? If we have two independent sources or an extended source from which S1 and S2 are derived, S1 and S2 are derived, then delta phi will vary with the time. At different times delta phi will vary, because the light which is emitted from here has no phase relationship with the light which is emitted by the other source. These are independent sources. If there is an extended source, different parts of the source independently give out light, and therefore, there is no phase relationship and phase varies with the time. So, that is what I have stated here, that if S1 and S2 are two independent sources or derived from an extended source, then delta phi will be a function of delta phi will be equal to delta phi of t. It is a function of time, because there is no phase relationship between the two sources. So, with this let us understand, let us come back to the, so I have described both the sources, and therefore, what would be the interference intensity. So, we have derived the expression for intensity, I is equal to 4 times I 0 into cos square delta by 2, cos square delta by 2. Delta here is changing with time. So, delta, where delta is now a function of time, this is the phase difference. So, this delta contains a path difference plus, so this delta contains a phase term due to path difference. This is fixed, this is not changing, but there is a second phase difference term delta phi which is a function of time, and therefore, delta will be a function of time, and this delta phi is varying randomly or rapidly with the time, and therefore, this function, to see the intensity we have to take average of this rapidly varying cos square function. Delta is randomly or rapidly varying, and therefore, we have to write intensity I is equal to 4 times I 0 into time average of cos square delta by 2. And we have already discussed that this time average is nothing but half. In the earlier class, we have discussed that time average of a rapidly varying term is half, cos square term is half, because cos square varies between 0 and 1, and therefore, I is equal to 2 times I 0. I 0 is the intensity due to the individual sources, I is the intensity at any given point. So, now this is independent of the phase and therefore, independent of the path difference. What does this mean? This means that if I see here, so each of these two sources S1 and S2 here, the intensity of the source is I 0 here and I 0 here, then on the screen at any point here we have simply 2 times I 0. In other words, if I plot the intensity, this is the x direction, the screen. So, if I plot the intensity along the x direction here, I of x, x direction here, instead earlier we had very nice fringes here, maxima, minima, maxima, minima. Now, we simply have, so let me take a different color, show that this is 2 I 0. Compare this with what we had earlier with x, at x equal to 0 there was a maxima and then it was 4 times 0. So, we used to have intensity variation like this. So, this is when delta phi is not, so delta phi is a constant, and this is the case when delta phi varies rapidly with time, which means there is uniform intensity. In other words, we will not be able to see any fringes, there will be no sustained fringes, fringe pattern. Interference takes place, but the interference intensity distribution is varying so rapidly that we will not be able to see any fringe pattern. And therefore, the summary is, if we have incoherent sources. So, in the last lecture we had seen that there are two requirements for interference, that the first requirement is that the sources should be coherent or they must have a constant phase difference between them. And there is a second requirement. So, we have already shown that if the phase difference delta phi is changing with time, then we cannot have sustained interference fringes. So, that is, if the sources are incoherent, that is delta phi phase difference between them varies with time randomly, then we do not have any interference. The second requirement which we had pointed out is that the wavelength of the interfering sources must be the same. So, we take up the second issue now, and wavelength of interfering sources must be the same. So, let us look at this issue. So, let me take up two wavelengths, one blue and red. So, let me plot this with the time here. Here I have. So, I am now looking at interference. So, interference with two wavelengths, interference between two different wavelengths. Is it possible? That is what I want to see, two different wavelengths, lambdas. Let me write this, interference between two different. Is it possible? I am not saying that it is possible, I am saying I am discussing interference between two different wavelengths. So, let us look at the wavelengths here. So, the red wavelength starts like this. So, I am showing the amplitude variation with the time. So, this is with the time, amplitude variation, and the blue wavelength, it has a smaller wavelength. So, time or x. So, we know that the maxima to maxima, that is, this is the wavelength lambda. So, the phase here, if I write this as an amplitude a 1 into sine omega 1 t, omega 1 times t, sine omega 1 t, and for the blue one. So, this is red, and for the blue one this will vary more rapidly. So, we know that blue varies more rapidly because the wavelength is smaller, it will vary like this. If the phase here is 0, then this maxima here, the red maxima here corresponds to a phase of pi by 2, and the 0 here corresponds to a phase of pi, because when phase omega t is the phase, this is the phase phi, and phi equal to 0, the total amplitude psi 1 is equal to 0, and when phi is equal to pi by 2, the amplitude is maximum a 1, the displacement psi is maximum, again at pi it is 0, and so on. So, the phase points, if I were to plot this as phi, then this would be 3 pi by 2 point, and this would be correspondingly the 2 pi point. For the blue, if we see, because for the blue one we have psi 2 is equal to A 2, the amplitudes can be same or different, sin omega 2 times t. Now, omega is 2 pi times the frequency, omega is the angular frequency, omega 2 is equal to 2 pi times the frequency f2 of the blue line, and therefore, because the frequency corresponding to the blue wavelength is larger, because we know that the wavelength is smaller, blue is about 400 to 450 nanometer and red is around 650 nanometer. Therefore, the frequency is higher and therefore, this is oscillating rapidly, this is varying rapidly because this number is larger. In the same time, this varies rapidly, which means the point pi by 2 corresponds to this phase, and in terms of phase this will correspond to 3 pi by 2, this is pi and 2 pi. So, what is happening? There is a phase difference between the two waves and the phase difference is continuously changing with the time. If we look at any point, x, so if I plot as a function of x, if I look at any point, any position x, then between the blue, so blue is varying rapidly like this and red is varying slowly. So, red is the phase of the red is varying slowly. They of course, both of them are traveling with the same speed. If I consider this as vacuum or free space, they are traveling with the same speed, but the phase, if we take any plane, will be continuously changing because this is varying rapidly, that is varying slowly. So, if we see the phase phi, phi will be continuously changing. If I say that delta phi is the phase difference between phi blue minus phi red, then it is changing with the time. So, we can see from the expression here. So, we have A sin omega 1 t and A, let me assume the same amplitude or A 1 A 2 sin omega 2 t, This is the phase term of the first wave, this is the phase term of the second wave at any given point. So, I can, without loss of generality, I can write this as x is equal to 0 point, and therefore, that is why I have not written omega t minus k x, that term I have not written because I am looking at a particular point. And what is the phase difference? The phase difference between them, the delta phi. So, the delta phi will be equal to omega 2 t minus omega 1 t or omega 2 minus omega 1 into t. So, this will be continuously varying with time. So, omega 2 minus omega t. So, delta phi, we can see that delta phi is a function of time and it is varying very rapidly. Remember that omega 1 and omega 2 are light frequencies which are very big numbers. These numbers are very big numbers because the light frequency f1 and f2 of blue and red are of the order of approximately 10 to the power of 14 hertz, 2 into 10 power 14 hertz, 5 into 10 power 14 hertz and so on. Therefore, this is a huge number multiplied by time, which means delta phi is varying very rapidly and therefore, the phase is varying very rapidly. What this means is interference is possible. So, I simply write the conclusion here, interference is not possible, between two different wavelengths, That is why we had written different wavelengths. That is why we had written, this was the second requirement for interference. When we started interference, we had given two requirements. One is that the sources should be coherent or there has to be a constant phase difference between them, and the second is interfering waves must be of the same wavelength. Now, I want to take up a interference with a source of multiple wavelengths. Suppose a source, we just said that interference is not possible between two wavelengths, but if I have a source interference with a source emitting multiple wavelengths, for example, we pick up here, consider 3 different wavelengths 400 nanometer, 500 nanometer and 600 nanometer. One is near blue color, this is very close to green, and this is orange line. So, recall that blue interferes only with blue. In other words, blue will not interfere with green. We have just now discussed that the two different wavelengths do not interfere, but blue will interfere with blue, and therefore, if we see the interference in the double hole arrangement, due to blue color we will have fringes with fringe width beta is equal to 0.4 nanometer. I have assumed a distance d equal to 1 meter and the separation between S1 and S2 as 1 millimeter, typical numbers which we use in practice, and therefore, the fringe width is given by d by d into lambda. Substitute for lambda is equal to 400 nanometer, we get the fringe width 0.4 mm. If we substitute 500 nanometer, we get, so for the green we get 0.5 mm and for the orange color we have 0.6 millimeter. How would the fringes look like? So, let us see the diagram. So, the fringes look like this. So, what am I showing? I am showing the interference due to blue, interference due to green and interference due to red. If only red were present, then we would have got the intensity varying like this. This is the x direction, that is on the screen, varying like this. If I had only blue color, I would have got this, but with the multiple wavelengths such as white light, if I have white light, then it would have all colors from blue to red at the other end, from violet to red at the other end, and then we would have got interference due to each color here. How would it look like? But we see that at O here, at O, all of them have the maxima at the same point O, but the maxima of blue is here, the minima of red is here, and after some time we see that when blue is minimum, red is maximum. So, they are at the maximas are occurring at different positions. What will be the net sum? The intensities, the amplitudes will add in such a way that the, please see that the maxima and minima occur at different points for different wavelengths except the central maxima. It is the same position for all the colors. So, what to expect? The net effect. So, here I have the net effect which is shown here, which is white light interference pattern. So, it is a qualitative representation. So, I have qualitatively drawn this, that because all the colors are having the same position of maxima, at this point all the colors will be bright, will add up to have a white light, a bright white fringe, and that is what we have. I have simply plotted intensity as a function of x. So, this will be the central bright white maximum, and then because most of these are passing through minima here, there will be a dip in the intensity, total intensity, there will be a dip. Then we have the blue maxima, orange, green maxima and red maxima, and therefore, we have slight variations, bluish color, reddish color, and finally, of course, all of them vary in such a way that we simply have uniform illumination. This is the Young's first experiment when he did with sunlight. What you see, this is the first interference experiment of Young. He saw one bright fringe, some colors and then uniform illumination. It is then that he switched to the sodium lamp or the spirit lamp with the sodium salt sprinkled over the spirit lamp to see multiple fringes. So, what is the conclusion? The conclusion is that if you perform the experiment with white light, you will be able to locate the central fringe where the path difference is 0 and the phase difference is 0 for all the wavelengths. And therefore, the final conclusion is thus the central fringe can be easily identified and the fringe shift delta x due to a phase change delta phi can be measured accurately using white light interference. I had posed this question earlier, how therefore to determine the shift in the central fringe? The answer is from white light interference. Thank you.